let's get started. I see some familiar faces from previous tutorials and from previous years as well. So welcome everybody. Thanks for joining in. Network analysis is a topic that I really enjoy teaching. It's because it's something I picked up in grad school. I found that being able to think about data in terms of graphs and their relations is actually a pretty useful, it's a useful skill to have when I'm doing my data work, day-to-day data work. So I'm really excited to be able to share this with you. I think I've been doing this, I was talking with Bobak just now and counting how many times I've done this now. It's since Scipy 2015. So this is the 6th year or 5th year, I think, that I've done this here, and then I've done it at PyCon before as well. I was supposed to have a co-instructor, by the way, so Riddle is supposed to be here, but then he couldn't make it because apparently it wasn't US border issues. It was Belgian bureaucracy instead. Held him up, so he couldn't exit Belgium to begin with. It's not that he was, there's nothing wrong with the US border in this particular case. But nonetheless, he's a person to look out for. He's done a lot of good research in network science. Originally, I would have been TAing, but then now I'm back up again. So I hope he gets his chance next year and he's able to take over the teaching of the tutorial at conferences. He's definitely a person to look out for. All right? He did it this year at PyCon, and I was his TA. Okay, we're going to do, because this is a network analysis tutorial, we're all about networking, right? So I'd like to first have you all network with your neighbors by introducing yourself, saying hi, and telling something new about something that they might not know about you. So go ahead, do that. Okie dokes. All right. I hear the chatter dying down a little bit, so let's get on with that. You just networked with your neighbors. Neighbors are a very important term that I hope you'll remember, right, going forward. I'll just leave that out there for you all. Cool. Before we go on, I also want to just quickly introduce the two TAs, Bobak and Hannah. They will be there to help out with technical issues. Bobak has been in the tutorial before, so he knows the material. He has some familiarity with the material, and Hannah has seen it before as well. And so if you have technical questions and you're feeling a little shy, feel free to grab their attention so that they can come over and quietly help you. They'll also be, Bobak also mentioned he'll be monitoring the Slack channel for questions, so if you're feeling even more shy, you can always ping on Slack, okay? Cool? Are we okay with that? Thumbs up, thumbs down, thumbs up? Okay. Yes?
The lights of the screens, things.
These lights need to go off? There's a bit of glare?
Yeah.
Okay, let's handle that then. Where? Over there. Okay, thanks, Bobak. Okay.
I think you want this thing.
All right, so while they handle the lights, let's go on. And I've got a little pop quiz for everybody that I'd like you to talk with your neighbor a little bit. I've got this list comprehension on the screen. Okay, we got this list comprehension on the screen. I'd like you to brainstorm what are the possible, plausible data structures for S and my favorite things. Talk with your neighbor. 1 minute. Okay. I hear the chatter coming down. Any volunteers? Any volunteers? So Thomas, who I just met. A list of dictionaries. That could be right. Yeah. What else? Any alternatives?
Yeah. So my favorite thing is to be iterable.
Okay, so you must be able to iterate over it. Yep. Yep, that's right. So someone here has really good, deep knowledge of the Python internals. That's amazing. Any other?
I think that whatever contains S needs to allow S to be actionable. So I don't think my favorite things could be itself be a dictionary because you can't have the keys have to be actionable.
Yep, yeah, that's right. Well, sorry, no, sorry, no, actually, I take that back. My favorite things is the thing we're iterating over. So we can iterate over anything that has an iter method. There is no strict requirement on iterables, I think, that they have to be hashable. However, S is the thing in which we're indexing into, and we're getting an item from, and so S must be hashable. S's keys must be hashable. And so I sort of let it out like Thomas's answer, basically, that the simplest data structure you might think of for this one would be a list of dictionaries. So this is important to know because when we deal with graphs in Python and NetworkX, which is the package that we'll use to do network science stuff, this coding pattern where we have a list of dictionaries is a pretty common coding pattern. So you'll want to be able to make sure you are somewhat familiar with this, right? Don't worry if you don't feel familiar right now. By the end of this tutorial, you will, right? By the end of this tutorial, you will. All right, let's go on. So anyways, this is probably one sort of thing that you might want to, this is one example of what's there. Okay, so we're here on a network analysis tutorial, which means the object of interest that we're going to be studying is networks, or also known as graphs, all right? So let's think about this for a little moment. Where do you see networks in your day-to-day? Let's talk with your neighbor about that. Go for it, a minute or so. I hear the chatter dying down again, so that's awesome. That means there's some people who've come to some conclusions. I'm hoping to get a pretty diverse set of answers here. What kind of examples of networks do you see? So any volunteers? I need to see your hands up so I can tell.
I've thought about this driving around in West Texas. You see all the wind turbines, and I think about how they're collecting the energy, the electricity, and then they have to send it to a transformer.
Yeah, okay.
Way of transferring the energy.
So you have something that might look like this. Right? Yeah, basically. Okay. Any other examples?
Hurricane models have a irregular triangular mesh
Okay.
consisting of nodes and edges and faces.
Okay. So you get things like that. Okay. That's definitely an example of network, and I'm glad you brought up the terminology. There are nodes and edges inside here. Okay, yeah. So you've got like location, road, location. Okay. Anything else back there? Oh my, that's a deep one. Yes. You basically have a call graph, right? Yeah. I'm not going to draw that one, but I get the point. Yeah. Anything else? Someone from the biological sciences, which I'm working in. Oh yeah, molecules are graphs. So if I remember my chemistry well enough, that would be a benzene ring, or benzene molecule. Okay, cool. Yeah. Anyone else? Last one or two.
Beehive.
Beehives. That's the first time I've heard this. Would you like to elaborate?
Well, the hives as a sort of the beginning, middle, and end of the bees. It's the bees themselves. So it's their creation, it's their world, it's their everything. But they start from zero. They all work together somewhat anarchistically,
Okay.
and but highly structured.
Okay.
To the point where when they're developing the hive, they're all communicating using their wings and body shakes and whatnot.
Oh, wow.
Not only to say, oh, this is danger or we're in danger, but also this is where food is. This is where the queen is. This is all those things.
So at any moment of time, there's a communication network between the bees. Okay. I learn something every day. It's awesome. And back there.
If you're selling things online, you might have a hierarchy of products. I work at a grocery store. We have fresh foods. Along with fresh foods, you have produce. You have baked goods. And then you basically have like a spanning tree. As you go down this tree, you go to the
Yeah, that's a great example.
Treatment when actually spanning avenues that go, like something might be a juice or soda.
Right. Beverages, for example. You have the beverages. Yeah, cool. Great. So these are all examples of networks. Now, what's common between them? You'll notice I've drawn them in a very particular way. We've got, we've got circles and lines. And sorry, I didn't mean to no, okay, so, all right. That was not meant to trivialize the answer, right? So circles and lines are literally how we draw and express most graphs. More correctly and more accurately, we have nodes and edges. Every graph is comprised of two sets of things. We have a node set and an edge set, okay? So graphs are the other term for networks, and we have two sets. Sorry, I'm going to make this consistent. We have the node set, and we have the edge set, okay? And the node, so that means there's a set of things that we call the nodes, the circles in the graph, okay? And then we have the set of lines that exist between the circles. So what do the nodes represent? What do the nodes more generally represent? Or, well, actually, you know what? Let's take the location network, a road network, right, as an example. What would we call the nodes inside this road network graph? Okay, so they could be places or intersections. So in the road network, the node would be a place, an intersection. And what about the lines? What would the edges represent? The paths, or the roads that allow us to move from place to place. Right? What about in, well, we know about social networks, and I'm surprised nobody shouted that one out. In a social network, what would be our circles and dots? Yeah, so the people and their connections as defined by some action of like follow or be friends, friending, yeah, that's exactly. So we have people, and then we have their relationships. I want to use a social network example to actually illustrate another interesting property of graphs, all right? If we take two social networks, let's take Facebook and we have Twitter. If we take the Facebook graph, the nodes are people, right? Likewise in the Twitter graph, or maybe it's bots, but, well, we'll ignore the bots for the time being. People and their relationships. Now, in a Facebook graph, I'd like to ask about this edge that exists between the two nodes. Is there an inherent directionality to this edge? Why? Yeah, right, exactly. So the edge only exists if it's a mutual, because this edge is defined as a mutual edge. Once someone can send the friend request, right? But once someone accepts it, now the data that we store is that these two are just connected, and we don't worry so much about that. So you can either call it a bidirectional edge, or more simply put, you can just put a line between the two and call it an undirected edge, okay? A no direction edge. Now what about Twitter? Is Twitter inherently directed or undirected? And why is that the case? Pardon me? So the mode of interaction, the mode of establishing a relationship between two users is the relationship of I follow you. So X follows Y, right? That's generally how Twitter works. Okay, so now we've actually come to maybe a somewhat richer definition of a graph, right? A graph has a node set, that is the set of users inside a social network graph, or the set of places inside a road network. At the same time, a graph is comprised of edges that describe the relationships between the two. One more crucial point here is that the edges can be directed or undirected, right? And the fact that there is an inherent direction or not in the graph can change sometimes how we're modeling our data. How we're modeling our problem, right? So if our problem dictates for a directed graph, then we'll want to use a directed version of this graph. And Network X has the facilities to do so. We'll see that in a bit. Cool. Right. So with that, I'm going to switch back to notebook mode. And if you look down on notebook 1, you'll see a few learning outcomes from this tutorial. First off, most importantly, I'm hoping to get you all thinking in terms of relations between your data, data points, rather than just individual data points themselves. Secondly, and so that means thinking about your data in terms of graphs. Secondly, my hope is that by the end of this tutorial, you'll be able to use comfortably the NetworkX package, right? The NetworkX package is a great package for doing network science and dealing with graph data structures. My hope is you'll be able to do this in the Jupyter environment as well. I'm also, in this work tutorial, hoping to convey that your choice of visualization of a graph can really influence the kind of inferences you make on that graph. And so my hope is you will stop or never ever have to plot a hairball, and instead plot rational visualizations, and I'll introduce you to that concept as well. The final thing that I'm hoping that you'll be able to take home from this is the ability to think on a graph. And I really mean something specific here. That is to think as if you were a thing computing on a graph. That is to say, you know only a little bit about the local graph structure of this network, and you're trying to find your way on it. That's one example, okay? Thinking on a graph is very handy for programming computers to do things on the graph, to find paths from one place to another. And it's a very foundational skill. And if you can think on a graph, then suddenly you can reason through a whole bunch of network algorithms and not be constrained by the names that you already know, but now you can maybe even come up with your own graph searching or graph searching or finding algorithms, right? That help you to deal with your graph problems, right? So that is a very meta level useful skill to have. And my hope is by the end of this, through some exercises which are going to hurt your brain a little bit, you'll walk away with having at least tried some of these things. Okay, so this is by the way for it being the last tutorial of the Scipy series, like last session. I know you all aren't masochists by choice, but don't worry. I will try to soften the blow, but I do hope to put you through some brain wrangling to get to think through some of these problems, okay? Okie dokes. Right, so we're now going to move on to notebook number 2. So I'd like to invite you to open up notebook number 2. And in this notebook, what we will be doing is we'll be getting a familiarity with the NetworkX API and using the NetworkX API to help us answer some questions about a graph, all right? So go ahead, run that first cell, and run all the way to the cell before basic network statistics. This will give us so every notebook, by the way, every notebook that we've got inside here has one data set that sort of forms this anchoring data set that we'll use throughout that notebook. In this particular case, we have a data set that comes from a study of 7th grade students. Right? So these are kids that are, they were interviewed, and it contains their preferred classmates for 3 different activities, right? So there are 3 activities for the students to choose from, and there are 3 activities that these students had to do, and they had to choose for each of these 3 activities, which other student was their favorite to do the activity with, right? And so what are the nodes in this case? The nodes are the students. And what are the edges in this case? I like you, right? And a count of how many times, right? Okay, does that make sense? Cool. Whether it's possible that they could have chosen multiple students or not, that I don't exactly remember the details, but that could be possible. And so you can maybe say 2 students. I really can't choose between the 2 of them, so I just give 1 point for both of them. That might be something you'll observe. All right. So first things first, every time we get a graph, one thing you want to make sure you have a handle on is some basic graph statistics. And so if every graph object G in NetworkX land has a .nodes class method, okay? Has a .nodes class method. And if you run that line, g.nodes, oops, wow. Wow, holy smokes, I installed a whole bunch of things that I should have installed. You all should be able to do it, right? If you run g.nodes, then you will get back a thing that looks like nodes view with this list of nodes, like the students, right? And those would be the individual students that are inside the network. So if we want to know how many students are present, then we would do the length of this, right? So we pass g.nodes into the built-in length function, len function. We'll get back our answer. Are we okay with that? Cool? All right. So what I'd like you to do, all right. So first exercise, we actually did it. We len g of nodes. Now let's do the same thing for the edges, right? So there's edges in the graph, and so you can do g.edges, and you'll get back the number of relationships that are recorded inside there. So go ahead, run that cell. Okay. So can you then try the next exercise below, which is to write the single liner that tells us how many edges are present. This should not take you more than 10 to 15 seconds. Okay, and when you're done, give me a bored look so that I know you're done. Thumbs ups? Mm-hmm. You should have something like len of g.edges, and tell me if you have 376. Yep. All right, sounds right. Cool. So g.nodes gives you the node set. G.edges gives you the edge set. And then you can now extract out the summary statistics for the graph, which is number of nodes, number of edges. The technical point here is that the size of a graph, which is also known as the length of a graph in Python space, you can do len of g, and that will give you the mathematical definition of the size of a graph, which is the number of nodes. So that's their equivalent, right? Cool. So we can also store metadata on the nodes, right? So the way that this data is stored is as a dictionary data structure. So we've got the graph, we've got the node set, and on each node we keep a dictionary. That dictionary has a bunch of key value pairs. Those key value pairs are basically mappings. You can think of them as if they were like a data table, right? So we've got each node is one row, each key is a column, and then we have the value that's stored inside there, except now in Python space, in NetworkX space, we just use a dictionary data structure to store the whole thing. So if you want to access the list of nodes with their attributes, what you would do is then do g.nodes, but instead of leaving g.nodes empty, you would add a data equals true keyword inside there, okay? Data equals true, and that gives you a node view on the list of on the nodes plus their metadata dictionaries. So then we would pass that into the list built-in function to cast that as a list, and therefore we'll get a list of, well, let's see. If you run that cell, you will get back what? A list of tuples, right? Do you all see that on your own screens? A list of tuples. Now, tell me how many elements are in each tuple? 2. There are only 2 elements. What's the first element? It's the node. And what's the second element? The metadata dictionary. Okay? So g.nodes data equals true gives you back a 2-tuple, a list of 2 tuples. So what I'd like you to try to do is, well, we've got the gender of each of the students inside over there. So can you count the gender, count the number of male and female students that are inside this data set? So this is an exercise for about 3 minutes. If you're stuck, talk with your neighbors. We'll convene in a little bit, and give me a bored look when you're done. Okay, how many people are done with this? Give me a thumbs up. All right, we'll move on when we're about 60 to 80% quorum, okay? So we'll wait a few more minutes. If you're genuinely stuck with these exercises, always know that I will have the answers up on the whiteboards. You can on the screens, so you can always take a look at that. Or if you're deep in your computer, you can actually just open up the instructor version of the notebook and take a peek at the answer there. All right? There's no such thing as cheating in this tutorial. Okay, how are we doing? Just wanted one more pulse check before I make a final decision. How many are done? Thumbs up, please. Okay, we're at about 60%. So I'm willing to go on, but don't worry, we'll walk through the answer, okay? So I suggested in the hint that you may want to use the counter object, right? What the counter object does is it takes in a list of items or an iterable of items, and then it'll return the number of times that an item showed up, each unique item, the counts of each unique item inside the list, right? So and then it returns a dictionary, with the key being the item itself and the value being the counts, the number of times that it showed up. Okay, so that's what the counter object does. How do you get the counter object? How do you get the data into the right shape to for the counter object to do its magic? Well, first you have to be able to extract out the gender of each student from that list of nodes plus their metadata. So the way we do this is we use a list comprehension over the g.nodes, data equals true thing, right? And we use that. We do the tuple unpacking, right? So there's a 2-tuple that shows up when we can unpack it directly in the for loop part of this list comprehension. So we have the node and the metadata dictionary, but we're not interested in the metadata dictionary itself. We're only interested in the metadata dictionary whose the value for gender in that metadata dictionary. Okay, so that's how we construct this list comprehension. That then goes into the counter object, that then returns us the number of counts per for each of the male and female. Okay. So then, if you ran the cell and you found you executed the test function, test answer, you'll find that we've gotten a few tests inside there for correctness of the answer. Writing tests, by the way, are a generally good thing to do. How many of you work as your day job as like software people and have to write tests? Yeah, exactly. So, and you know then the importance, right? So if something goes wrong or I make a modification to the code base, then an automatic test suite that like runs every test that I've pre-specified beforehand is a very useful way of capturing any inadvertent bugs that may have shown up that I wasn't ready to catch by manual checking. Okay. In data, it's a little harder to write tests for our data science code because oftentimes it's a one-off analysis and stuff. If you want to, you can catch a talk by Jess Ford, Jes Ford. She did a talk this year at PyCon on testing, right? Testing for data scientists. And I think for those of you whose day job is data related, that's a very useful talk to catch, okay? We screened it at work. Like we watch YouTube videos over lunch at work, and so it's like pretty awesome. So hers was one of the talks I had picked for the playlist. Cool. So likewise, we have nodes with their metadata dictionary, and edges can also store metadata as well. So if you do g.edges data equals true, what you'll get, and you cast this into a list, what you'll get is basically a list of, now is this, how many elements in this tuple? There are 3 elements, not 2 elements. And why are there 3 elements? What's the first and second one? These are the nodes, exactly. So these are the nodes that this edge belongs to. And what's the third element? The metadata, exactly. Right? So what I'd like you to do is to try out the next exercise below, which is to figure out the maximum number of times that any student rated another student as their favorite. We know the answer already, but place this in a testing framework. This is a property that we need to guarantee of our data. So if there's something that was recorded as minus 99, that would be bad. If there was something that was recorded as 4, that would be bad. So here we're testing for what's the maximum number. We haven't written a test for the minimum. But try this out. Try this exercise out. Okay, quick spot check. How many people are done? Okay, we're roughly at quorum. So let's move on. Same thing, same logic as before. You need to write a list comprehension over g.edges with data equals true in order to get out the list of numbers that are present inside the graph. And then you can do your test here that says make sure that the max count is equal to 3. All right? Are we okay? Any questions on this so far? No issue? All right. Let's move on. So first 2 exercises really were all mainly about how do you query the graph for properties of the graph. What's the size, how many nodes, how many edges, as well as properties of the individual edges and the individual nodes, right? That's how you can write queries on a NetworkX graph. The next thing that we're going to do is how do we manipulate and edit the graph? How do we add nodes and maybe remove nodes? Well, there's a remove node counterpart to everything that we've done, but we're going to try to manipulate the graph by adding nodes into it and adding edges into it. So let's add 2 students. They turned out to be left out. If you look at the prompt there, they're individual number 30 and individual number 31. They love hanging out with individual 7, so they sort of said, okay, in all 3 activities, it's the 3 of us, right? It's just, sorry, in all 3 activities, it's, yeah, I nominate those 2. We forgot to record them. So I'd like to have you add that data into the graph. Got some starter example code there, so make sure you do that. Little pointer, this graph, is it inherently directed or undirected? It is directed. All right, so that means if you add one edge one way, you won't get back the automatic edge added the other way. Okay, a little hint for this activity. Alrighty, so in the interest of time, I'm going to move on, but I hope the API, which is the main point here, it becomes clear to you. All right, so there's the add node class method. One thing that's really nice is any keyword arguments that you pass in after the thing that represents the node, whether it's the number, the ID, or the name of the student, anything that you pass in after that automatically becomes part of the metadata dictionary. Okay? Are we okay with that? Okay? And there's a likewise the add edge counterpart. So you can add an edge between two nodes. If one of the nodes doesn't exist, network X will actually just silently add it. So this is a very important point for you to keep note in. So if you intend to have nodes that have metadata, but then you don't pre-add them first, you will just end up with nodes that are, in this case, the integer without the metadata dictionary. Right? So a little safeguard for you guys. And then we have the count equals 3, which is a part of the keyword arguments that happen after the first 2 arguments that we pass in. And anything that's after, likewise, gets automatically part of the metadata dictionary. Any questions so far? No? No? Okay, all good? Cool. So now, basically, you've got the ability to query a graph, interrogate what nodes and what edges are present, as well as pull out metadata from each of the nodes and the edges. All right? Okay, so there is one more exercise which I originally labeled as break time exercise, but I actually think it's a really fun exercise. Can you find in the graph unrequited friendships? So give that a shot. Like, spend about 5 minutes or so. Think about this problem, how you would approach it. Okay? Okay, how are we doing? How many people are done? All right. I'm going to erase this answer, set pseudo, and type it out from scratch so that we can go through a little bit of the logic, and then show the key thing that we need to know is we can actually query a graph to see whether it has an edge or not, right? So if we want to grab all of the so-called unrequited friendships, that is, I say I like you, but then you don't say you like me, right? So, right? So here's how we would do it. Unrequited friendships. We'll initialize a list. We'll collect all of them together and just finally at the end get the length of that list. All right? So we know we can iterate over the list of over all of the edges in a graph. So we'll do n1, n2 in g.edges. Okay, that's what we're doing that first line. First thing we'll do is we'll actually check, does the reverse edge also exist? Right? For every single edge, does the reverse edge exist? So if not, g.has edge n2, n1. Okay, that's the key piece in this for loop. Then we'll append the tuple n1, n2, and at the end, find out what the length of unrequited friendships is. Okay? Simple walkthrough to hopefully demystify what's going on. Really, the key line here is that this guy, g.hasEdge, what it returns is a Boolean, true or false. And so then you can take advantage of this Boolean to say, all right, if I have an edge going that way, but I don't have the reverse edge, then we'll consider that an unrequited friendship. Okay? Any questions so far? All right, cool. Let's move on then. By the way, if you look at the instructor notebooks, there's this really smart idea that involves sets and reverse links and two sets and set differences and stuff. I encourage you to take a look at that. It's pretty cool. All right, so if you scroll down on notebook 2, you'll notice we used a lot of this list comprehension type of programming pattern, right? And we took advantage of a lot of tuple and packing to help us reduce the amount of code that we're writing. Okay, so we've got this going on inside there. What I want to move on now, so basically now at this point, you basically should have a good grasp of the Network X API. Once you have this grasp of the Network X API, it becomes much, much easier to manipulate graphs in memory. All right, now I want to move on to a slightly less brain-burning activity, which is looking at pictures of graphs, right? There are a few ways that you can draw graphs. The built-in nx.draw method will, under certain circumstances, actually give you back a hairball. All right? Can I ask what you can interpret from this hairball? When you see this hairball, what do you see? Like what inferences about the graph do you see? Well, okay, you know what? Some people might be a bit shy, so talk with your neighbors for a minute. Okay, do we have some brave souls willing to share what they thought? I remember back there was back there. I think John, you had an answer, and then up front. So you want to start first? Thank you. That's the correct answer.
There's some outliers.
There are some outliers. Okay, like this one and maybe that one, right? What else? Anything else? You got? Sorry?
Introverts on the outside and extroverts on the inside.
Maybe. I don't know. Well, these three, those three kids we just added, are they really introverts?
Those two guys, maybe they're just the nerds in the line.
Me. Maybe so. Sorry?
So they're just new to the class.
Okay, maybe so. Maybe that's what's happening as well. What is true though is what is definitely true is John's inference, and that is we know that there's a bunch of students and there's a bunch of relationships, and we can't confidently tell much else. Yeah, sure. Which one is 31 and 30? Those two, right? Yeah, we couldn't be any more precise than that. Yeah. So one thing about drawing graphs, okay? Graphs are inherently high-dimensional objects. I'm just going to leave that statement there and not clarify it, but if you take a high-dimensional object and you want to project it onto a two-dimensional plane, you're going to be left with a lot of choices on how to lay things out on that two-dimensional plane, okay? The default algorithm for nx.draw, I think, is a spring layout, which involves some form of like force-directed kind of thing that goes in there. So it's, or Kamada Kawai actually is the force-directed. I think that's the default. I'm not exactly sure, but you can tell that there's this thing where it's like things that are, if we have a high density of edges between nodes, then we'll have things clumping together. And then we have low density of edges, then we'll have them on the outskirts, right? That's sort of like the general thing. But then you really can't make much inference on that. And it's also non-deterministic. I run it once, it looks like this. I run it again, it looks different. There you go, right? So you can never guarantee that you'll get a so-called reproducible plot. I mean, yes, the graph data hasn't changed, but you can't do an automatic test that says like, load this plot, load that other plot, and make sure they're like identical with NumPy, right? You can't do that. So this form of layout, while it's good as, say, a first pass, just to get a quick view onto the data, it's not the kind of thing that you want to be working with, okay? So what I did with one or two other people was build a package called NXViz, which basically is a nice API on top of NX NetworkX plus Matplotlib, and sort of gives us a way of declaring how we want to visualize our plot without prescribing exactly how it's supposed to happen. Okay, so one way that we can visualize a graph is actually by a matrix plot, right? And why is this possible? Well, it's possible because if we do this thing, actually I'm going to switch over to drawing mode again. You can see this on your notebooks, so don't worry about that. I'm going to switch over to drawing mode. If you take the nodes, if you have a graph and you take the nodes and lay them out along the edges of, along the sides of a matrix, you can actually build what we would call an adjacency matrix. Okay, so let's say we have a graph that looks like this: 1, 2, 3, 1, 2, 3, and the graph was like that: 1, 2, 3. We would fill in the entries into that matrix according to whether an edge existed between the two. So can you tell me, in this graph, in this table out here, which elements should be filled with a 1? 1, 3, 1, 3, as well as 2, 3. So 2, 3, 2, 3, right? What's something that you will notice immediately? Look at symmetries of sorts. Yes. Yes, very good point. Undirected graphs have a symmetric adjacency matrix. And we say symmetric along the diagonal. Okay? So this is one way of taking a look at your graphs. So now if we switch back to the notebooks, take a look at that adjacency matrix that you have there. Is it symmetric? Nope, it isn't. Under what circumstances, and we know it's not symmetric because there are unrequited friendships inside there, right? Under what circumstances would a directed graph have a symmetric adjacency matrix? I hear murmurs. Do we have someone who's willing to? That's right. So where there is basically a bidirectional edge between, so for every edge that goes one way, the other edge also exists. And under that circumstance, we will have a bidirectional, we will have a symmetric adjacency matrix. Okay? Are we okay so far? Cool. So this is one way of visualizing. One other thing you might notice in this guy, okay, is what about the diagonals? Are the diagonals filled? No, right? Yeah, and I personally feel very good about that because some German leader at some point in time said, well, I want to raise a generation of narcissists and fearless and whatever, right? Like we don't have narcissists in this crowd. No kid said, I only like to play with myself for an activity. So that's good. That's very good. Like we can rejoice for humanity, at least on this data set. Okay? So that's another important point though. Self loops. Do we allow edges that go from one node and return to that same node? Under some circumstances, self loops can be useful as a data model. In this particular case, though, a self loop not only would be kind of nonsensical, it would be also kind of emotionally worrying, right? So yes, so self loops don't exist in this particular data set, and that's something that sort of makes sense. It's like a qualitative test that the data are correct. Cool, so that's the matrix plot. Next up, we have this thing called, what I would now call rational vises that involve circles and lines, all right? And the matrix plot just puts all of the nodes on the rows and columns of that matrix. We can instead do a thing where we order all of the nodes, or we place all of the nodes on a single line, and then we draw arcs between them, okay? And if we draw that way, well, suddenly we can now make inferences on the structure of the data, right? So what do you see about here? Well, so first off, we don't show any direction, and that's partly an artifact. That's, I think, a missing feature in NXVis for which I'd love to see a contribution, okay? What else? We've colored the nodes by their gender, or colored the nodes by the gender that's attached on there. So what do you see? Or something else as well? Yeah. Yeah, these are like the really popular girls or something, right? Yeah, okay. What else? So first question, actually, let me backtrack a little bit. Could you have seen that even if you colored in the hairballs? Maybe, maybe not, right? This sort of visual inference is much more readily available if you first, what you do is you order, you find a logical placing and a logical ordering for the nodes, and then you figure out how to draw lines between them. So in this case, what we're doing is basically prioritizing node placement over prioritizing the edges. Okay, and this is what helps us draw rational visualizations. So the arc plot is one particular plot, and then there's the Circos plot, which is basically all we're doing. We're taking the two ends of the arc plot and joining them together. All right, are we okay with that? So that's just simply another visualization that you can use. Now, there's one other really nice and neat plot, which is the hive plot. And I really like this one, but it's been a bit of a struggle to get this into NXViz. And it's been a struggle for 3 years, partly because I don't have time, and partly because the layout algorithm is kind of interesting. And my first implementation has been hard to move over to the new package. But I still have it in an independent .py file that you all can grab down. And it works like this. Okay, so you take a look at this. We've got the two groups. Okay, we've got the two groups of students. We've grouped them by that. What the hive plot allows us to do is to take a single group and visualize both the intra-group, that's the stuff at the 12 o'clock and the 6 o'clock positions, the edges there. It lets us visualize the intra-group as well as the intergroup relationships. Okay? So this actually brings a lot more clarity compared to, say, the Circos plot or the arc plot. It brings a lot more clarity onto the number of intra-group relationships versus the number of intergroup relationships. Okay, and we use that. I use that in this plot in grad school to help interpret some influenza data where we're looking at like movement of genes between influenza subtypes. And we had these like intra-subtype movements and inter-subtype movements. Okay. Yes. So what happens if you have 5 different groups? If you have 5 different groups, then what you would do is you would actually do 5 choose 3 number of these plots. So a hive plot at most can handle 3 separate group axes. Okay? Any more and you're not able to, it's kind of difficult to show the relationships between, say, like you can draw it out for yourself. If you have 4 group axes, it's hard to draw the top one to the bottom one or the right one to the left one. You have to go around. So at most 3, okay, at most 3. But you can now create a hive panel which shows one set of 3, another set of 3, and a third set of 3, and so on, a fourth one, and fifth one, okay? So then that's the way that we would construct a hive panel, a panel of hive plots. Does that answer the question? Okay, cool. All right, how are we doing so far? Okay? All right, any questions, any other questions before we move on? Okay, we're gonna take a 10-minute break at this point. We'll come back at 2:50, and we'll continue on with notebook number 3. Okay, it's 2:50, so let's get started. In notebook 3, the general level question that we're going to try to answer here is how do we figure out what are important nodes in a graph, right? How do we figure out what are important nodes in a graph? And why might that be important? Well, infectious diseases is one great application, right? In my previous professional life, I worked in infectious disease research in grad school. We were talking about the flu and how flu evolves and the likes. One really important thing is when you have an infectious agent and it's spreading through a population, the contact network, right, can be of extreme importance. Knowing who was in contact with who can be really important for figuring out how to stop further spread of that infectious agent. Okay. So we're going to load, this time around, a different data set. This data set is called the Socio-Patterns Network. It's from the Connect website, and it describes the face-to-face behavior of people at an exhibit. Turns out it was an infectious disease exhibit, so it's perfect. Basically, people came in, and if there was someone recording, Big Brother style, whether they had a 20-second or longer face-to-face contact, right? So far, so good. So we can build a graph out of it. And so what here would be the nodes and what would be the edges? Nodes would be people, and edges would be face-to-face contact for more than 20 seconds. Absolutely. And is this directed or undirected? like if someone has face-to-face contact with you for 20 seconds, you can't really control that, right? Except doing this, right? So yeah. But it would be kind of socially rude if that happened as well. Okay, so let's go ahead and load that data. And once again, let's make sure we have the summary stats of this graph out there. So we have 410 nodes and 2,765 edges, all right? So first things first, how would you evaluate the importance of a node in a network? Let's think about this. Let's assume for a moment that this social patterns data set was an infectious disease data set. Okay? How would you evaluate the importance of a particular node inside this graph? Sorry, so hands.
Number of edges.
Number of edges connected to the node. Okay, that's great. Now, do you remember right at the beginning, you all built a graph yourself amongst each other, right? Networking with one another. And I said, network with your neighbors. Neighbors is the term. The neighbors of a node are the nodes that are connected to that particular node by an edge. Okay, so the number of edges and the number of nodes, they are equivalent ideas. All right? So in NetworkX, every graph has a class method called .neighbors. And if you pass in a particular node, it will return back the neighbors of that node. Okay, so we can do something like g.neighbors, and that will give us a dictionary key iterator. So they're not returning us the thing yet. It's a lazy evaluation type of thing. If we pass it into a list, now suddenly we have all of the nodes that node number 7 is connected to. And so the length of this guy would be 7. All right? Are we okay with this so far? That's how we can find out how many neighbors each node has. So the next exercise for you is to go and figure out which node has the most number of neighbors, and actually rank all of the nodes by the number of neighbors that they have. Right? So spend 5 minutes or so on this. If you run into trouble, talk with your neighbors, pun intended. Otherwise, take a look at the instructor notebook. Okay, one more spot check. How many of you are done with this exercise? Please give me a thumbs up, real high. Okay, great. So we're at quorum, and I'll just very quickly talk through the one possible answer. A bunch of people have come up with multiple different answers for this, and if you look at the instructor version of the notebook, you can see their provided solutions inside there. Okay, the solution that I first implemented was to use the sorted function. Okay, and what we're interested in sorting is g.nodes, but the way we want to sort it is by their length, the length of their list of neighbors. So we use a key is a function, a lambda function inside there. Okay, so and what that does is that gives us essentially a mapping between each node and the number of neighbors that they have, and then we're sorting them by the number of neighbors that they have in reverse order. Now, one other solution that I thought was pretty neat, because it hints at some of the things that we'll talk about later, is that you can actually cast the whole thing inside a pandas series. All right, so all you do is you create a mapping of node ID to the number of neighbors that they have, make that into a pandas series, and simply sort the values. So you don't have to worry about key equals some weird lambda function over there. So that's an alternative way of handling this. Okay? Any questions so far? No? Okay, let's move on. So the number of neighbors is one way of identifying an important node, right? So that node is important because they're in contact with a lot of other nodes. And on this definition, we actually can create a centrality metric. We can define a centrality metric, which is the number of nodes that I'm connected to divided by the total number of nodes that I could possibly be connected to. And so if we have two graphs that have different numbers of nodes, but are from roughly the different absolute number of nodes, but came from the same graph distribution, then we can actually compare them we can compare them in a way that's that's a fair comparison. All right, we can compare them in a fair comparison because the number of nodes might vary because of graph size. However, the centrality metric is a normalized metric. So the degree centrality, I want to talk with you all about this. Degree centrality, if it's divided by the number of nodes that I could possibly be in connection with, then what is that denominator? What is that denominator? Like, if I have n nodes in a graph, then it is going to be n minus 1. But there's one special case where this doesn't hold. And so what is that special case? Yes, we are allowing self loops in which the number of nodes that I could be connected to includes myself, and therefore the denominator in that case would be n, all right? Very important thing to remember. So when you're looking at the centrality metrics from a library, from a graph library, make sure you're double checking whether it assumes self loops are allowed or self loops are not allowed. Okay, so network X provides such a function. It's called nx.degree centrality of G. And what it will do is it will give back a dictionary. And in that dictionary, the keys are the nodes and the values are the degree centrality, right? Nothing too difficult there. So what I'd like to do next is do a little bit of graph statistics. The distribution of degree centralities, or the distribution of degrees, is an important thing for us to quantify inside there. Now, how many of you have heard my rant about ECDFs? Yeah. You know how much I prefer ECDFs to histograms. Like we say distributions, and first thing you might think is, oh, let me just plot the histogram of let me plot the histogram of the whatever thing we're trying to visualize the distribution for. I have argued and ranted in many places saying that ECDFs, or empirical cumulative distribution functions, these provide much richer statistical information than can a histogram, because histograms can be subject to binning bias, and you can lie with histograms. It's very hard to lie with ECDFs because you have to show all of the data. Whereas in a histogram, you have to bin things, group things into bins, and the way you group things can also obscure data. It can obscure by modality and such. So I really don't advocate for visualizing things with ECDFs. So I'd like you to try the exercises below to plot at least the ECDF of the degree centrality or the number of neighbors that they have. Okay, so give that a shot. Oh, wow, okay. So I just realized I completely obscured the implementation of the ECDF function inside a custom module. So I'm going to actually break out a little bit ECDF and put, if you do something like this, by the way, inside the Jupyter Notebook, where you put double question mark after a particular function name, you'll actually get the full source code plus the function signature so that you know what the return is, what it accepts. So if you do that on your notebooks, what the ECDF function is doing over here is it's giving you the thing that you can plot. It's giving you the X and Y data that you can plot inside plt.scatter, basically. But what you must pass in is a single iterable of data that you want, for which you want to plot the ECDF. Okay, so I just want to make sure that that function is demystified for you. Okay. So spot check. How many of you've got this chart? Okay. I don't want to dwell too long on the exact details of the chart, but I just want to, for the benefit of you who haven't heard the rant on ECDFs, I'm going to switch to drawing mode so that you all can see why I think ECDFs are better. Okay. So let's let that come up on the screen. If you've got data, okay, and I asked you, and I plot, say, the histogram, or in this case, I'm just going to plot an approximate density of the histogram. Can you tell me where's the central tendency of this data? It's not a trick question. Right where it's tall, right? So at that value over there. What about the bounds of the data? The ends, is it here and here? Really? Do we know the exact value? Can we know the exact value from the KDE? kernel density estimate or histogram? No. Why? Because if we did the histogram, we'd have bins, right? Etc. And we don't know within this bin which value exactly is the minimum value. And likewise, on the tails, we don't know exactly which value in that bin is the tail value. Okay, so it's very, very hard to tell. And if I change the bin size, I can totally lie about the bounds of the data, right? And lie about the central tendency as well. So here's where the ECDF comes in. What we do with the ECDF is we plot every data point inside that distribution, but we also plot on the x-axis, and on the x-axis is the value that that data point is, and on the y-axis it is the cumulative fraction of data points that fall at that value or below. Okay? So effectively, you'll get something that looks like that. Now, I drew it as a line, but in reality, it's comprised of a whole bunch of dots. Okay? All the way down to here. Can you tell me where the central tendency of this data is? Exactly. Where y is equal to 0.5, we draw a line over to here and ask what value on the x-axis does that take? That gives us mean, median, or mode. Median. It gives us the median, and it gives us a very nice, robust central tendency measure. Next, where are the bounds of the data? The first data point and the last data point. Exactly. You could not hide this with this ECDF, right? There's no way to hide the bounds of the data. So by the way, if instead we had outliers like that, if I did the right bin size, I could totally hide them. I can't hide them with an ECDF. So if you want to be an honest data scientist, use an ECDF. Okay? Now, if you want to communicate with your stakeholders, however, that's a different story. They don't understand histograms typically. They don't understand ECDFs typically. They understand histograms. So what I would do is I would actually plot both of them, show them both. Here's the histogram, so you roughly get an idea of what the shape of the data are. And now here's a lot of rich statistical data that you can look at from the ECDF right next to it. Okay? Recommend that you plot both of those. Not only that, can you tell me what the interquartile range is? Of course you can. Get the 0.75, get the 0.25, draw it over, and suddenly you've got your interquartile range, this bound over here, right? So ECDFs, they really are awesome. And the final thing, can you plot two histograms over one another without obscuring information? Kind of difficult, right? Like if I had that histogram and I had the red histogram, and if I did some bad things with matplotlib and made one kind of opaque and the other not so opaque, then like, well, okay, if I did this, by the way, then suddenly the black histogram is completely, like a large portion of the black histogram is obscured. On the other hand, I can plot two distributions of data very cleanly on the same plot. High density of information for low ink, that's great value for ink, okay? All right, so enough on the rant on ECDFs. I just want to make sure you have that concept inside. We'll switch back to the notebooks. And let's do a bit of interpretation then on the ECDFs that you get for the degree centralities. What do you see? The right-hand side. Just look at the right-hand side. Or in your own notebooks. You have them. You should have them on your notebooks as well. Pardon me? 3031.7? No, we're not on that graph anymore. We've changed graphs. What do you see? Okay, so first question, are there outliers? Potentially, this guy, right? those three, sorry, right? Those three are potentially the outliers in the data set. Let's see, what else? Does this look normally distributed? How would you tell? Yes, yes. Gaussian distributed data look very sigmoidal, S-shaped, when you plot the ECDFs, okay? You don't see the classic S shape over here, so we probably wouldn't want to fit a normal distribution to the degree distribution of on this graph, right? Okay, cool. Next question: degree centralities and number of neighbors. Do you expect them to have identical ECDFs? Or really similar? Sorry, really similar ECDFs. Pardon me? Exactly the same shape. Yes, the x-axis is the only thing that changes here. Okay, and that comes from the mathematical definition of degree centrality. Cool. So I don't want to harp on that too much. The next exercise I'd like you to do is to visualize this graph, and then we'll do some visual inferences on that. The API, by the way, is shown up there in line, so you should not have to wrestle too much with finding the docs, okay? Okay, so how many of you have the graph, have the visual of the graph on your screens now? And how many of you want to share something that you've learned about this graph? Yeah. Okay, cool. Can I just challenge myself to nx.draw of G? I mean, could you tell that from this? No. Yeah, that's a hairball. So yes, that's definitely one of the more obvious points that we can grok from this chart, from this visualization. That is, if we order the nodes along the circumference of the circle by the time or the order at which the nodes came in, and we take order as a proxy for time, then you'll notice most of the edges occur between nodes that are very close in proximity to one another. They don't occur, very few edges occur across time. This person here probably stayed for quite a while, right, inside that exhibit. And this person over here also, stayed for quite a while as well, right, inside the exhibit. So you might be able to, if we had the exact times, then from the graph, if we had exact time of entry for that graph, right, then, we would be able to deduce from the graph the length of time that node was present inside the exhibit, right? We just have to do a few more calculations on top of the metadata in order to extract that information. Okay? Any questions so far? Okay. If not, let's move on. We're going to take a slight detour and talk about paths in a network, okay? And the reason paths in a network is such an important idea is because, one, it will allow you if you are able to reason about paths on a network and how to find paths and how to find a path between this node and that node, that's practice thinking on a graph, okay? Thinking on a graph. Secondly, we'll actually use paths to help us arrive at a different definition of a really important node, right? And we'll get to that in a moment. So one thing that's really important is about finding the shortest path between two nodes in a graph, okay? This is a classic computer science, second or third year computer science kind of problem that you would be asked to solve if you're in an undergrad program. And so if you want to find the shortest path between any pair of nodes in a graph, how might you do it? One particular algorithm is called the breadth first search algorithm, okay? And it's not necessarily the fastest, but conceptually it's like one of the best ways to learn how to think on a graph, because once you've implemented the breadth first search algorithm once, it's like biking. You never forget how to think on a graph after that, okay? So I'd like you to attempt this next exercise, which is to implement the breadth first search algorithm by implementing it inside the path exists function, okay? And it's all it does though, it only says is there a path between this node and that node? I'm not going to impose the hard restriction that you must find the shortest path, okay? But we're going to take advantage of the breadth first search algorithm to find out, is it possible to get from one node to another node on the graph? So I'd like you to take some time to do that. This one is an exercise that does require some thinking through the problem. All right, and you might need to talk with your neighbor. You might need to get some paper. If you need paper, we've got paper over here. There's pens up front. Babak can help with getting pens to you if you need it. Just let us know, okay? We'll spend about 15 minutes on this problem. And if we don't reach 60% quorum, that's totally fine. The whole objective is that you should have practiced going through and trying this out for yourself. Okay, got a bug pointed out by one of our participants. Make sure you cast g.neighbors inside a list, because otherwise that generator gets consumed and you won't be able to. Yeah. That's right. It used to be a big blank cell. Later on, like this whole part, I just like I would have given you just this, right? Recently we changed it, so now they're all filled in with nice like prompts that are easy to follow. Right, so how many are done again? Sorry, just let me recap. Okay, good, right, we're good. So I hope having seen through at least this part, it makes it clear, right? How we're working through a breadth first search, right? Essentially, all we know is the current local structure in the graph. So I have to start at my query node, right? The start node, and I just ask in layers of onions around that node. But in order to do that, I need to know first who are the neighbors of this particular node. Then I go over each of those other neighbors and ask who are their neighbors until I find one of those neighbors is my destination node. But along the way, we also have to keep track that we're not revisiting nodes that we've already visited before, right? That's a very key thing. Otherwise, you, the poor computer, thinking on the graph, will end up going ping-ponging between nodes that you've already visited, and that's completely extraneous. There's extra work for you. Okay? Are we all right? All right, any questions on this? So far, so good? All right. Let's move on. Now, I made you fill in a function, but it's already implemented, so I apologize. NetworkX already has a function called hasPath. So you can do nx.hasPath in graph G and pass in the two nodes, and it'll give you a Boolean true or false whether that path exists between the two nodes. And you can actually use this in pretty productive ways. Right? You can also use other NetworkX graph functions to build up higher order queries. We'll do a little bit of that in the next exercise. So for example, I want to know, does it have a path? Okay, so we can do nx.hasPath as a Boolean check, and then if it does have a path, we may want to like return that shortest path and just visualize that guy rather than the whole graph together. So we may want to be able to extract out particular subsets of the graph, right? And so that's what we're going to do next. Okay, we're going to do that next. So the next exercise is an exercise in really just composing NetworkX functions together, right, such that we're able to do higher order queries and do interesting things and maybe even use them for visualization purposes. Okay, so try that next exercise below. Okay, how many of you have something that looks like this? Right, you're able to extract out the subgraph by composing basically NetworkX queries together, that the elementary NetworkX queries on the graph. All right? Questions? Yes?
Draw does not seem to draw the same orientation or shape
Yep.
between different.
That's right. So the question for the benefit of YouTubers later is that one thing that we notice is nx.draw is non-deterministic. And that is absolutely correct. The drawing algorithm is non-deterministic. And so that means you saw it just now, like for yourself as well, if like you run that cell twice or thrice, the orientation may change. And that's, frankly, I think it's a problem for reproducibility of your visualizations. So that's part of, again, the motivation of building NXViz, being that we're able to now control the positioning of the nodes, and rather than leave it to random chance where they go. And so as a result, we now have more stability on the visualization. So that's something to look out for when using nx.draw. However, you can see for these like one-off little things, sure, why not, right? And especially if the graph is small, as a rule of thumb, if it's less than, say, 7 to 12 nodes, and you're just looking at a local portion of a graph, then sure, totally, don't hesitate to do that. Are we okay? All right, let's move on. We're going to skip over all the challenge exercises. This is our stuff that I've decided would be good to do at home instead. We're going to revisit now this notion of an important node, okay? Because another way that we can define the importance of a node is to ask how many paths that are the shortest path between any pair of nodes, how many of those paths pass through a particular node. Can you think of a situation where that would be kind of like that would mark the importance of a node? Okay, how so? Like how would this shortest path thing come into play? Right. So these are the critical, so in a power grid, right, there are certain extremely important nodes, because in order for power to be transmitted from, say, one place to a group of places, if that node fails and gets cut off from the graph, suddenly no transmission of electricity can happen to the other receivers downstream of that particular node. Exactly. And so this is one really important place where like that node having a high betweenness centrality, this is what we call betweenness centrality, that node having a high betweenness centrality would mark its importance, okay? So I'd like you to, so betweenness centrality exists in network X, okay? So it's got this nx.betweenness centrality thing. Its data structure that it returns is identical to the degree centrality, so it'll return a dictionary where the keys are the nodes and the values are the metric itself. And so what we're going to do now, we'll code along this one. So go ahead, code along with me. We're going to plot degree centrality against betweenness centrality. Okay, so let's do this. So we'll get the degree centralities as a pandas series, and we'll get the betweenness centrality as a pandas series. And then we'll make a data frame of the two of them. And then we'll plot a scatter plot of the two. Did not import pandas. Apologies. Sorry, so the betweenness centrality, I forgot to mention that. So the betweenness centrality is the number of shortest paths between any pair of nodes that pass through that particular node, divided by the total number of shortest paths that exist in the graph. Are we okay with that? Okay. So if we do that, we should get a plot that looks something like this. Do you all have that? Something like that? Yeah? Okay, so what does this tell you? Are degree centrality and betweenness centrality well correlated? Not at all. Not at all. Can you think of an example where we would have a node that has a high between a centrality, but actually has a very low degree centrality? Sorry? The root of a tree. Well, now a tree is a directed graph. So if we assumed that the root of a tree, if we assumed that we converted the tree into an undirected data structure, then yes, the root of the tree would now suddenly have an extremely high between a centrality, but very low degree centrality. Is there a simpler case? Anybody? Back there? No? Okay. Let's try a barbell graph. Take a look at the barbell graph below. Right? On the barbell graph, that middle node in between the two bells of the barbell has a very low degree centrality because it's only got two neighbors. The others generally have 5 or more, right? But it has a very high between-us centrality. And that's because if you chopped off that, then suddenly the two communities of the bells are disconnected from one another. That sort of raises some philosophical things, right? I was thinking when I was making this exercise, I was thinking about how we rate people, like ratemyprofs.com has like a single thing that you can rate them on, or like maybe one or two. We humans tend to rate people on single axes, but nodes are humans, right? So in a social network, and there's multiple ways of assessing the importance of a node. We've only shown two. We've only shown two here. Right? There are multiple ways of assessing node importance. Likewise with humans, right? Like there's multiple ways of assessing how good a human is. So I hope this serves as a bit of a life lesson beyond just network science, right? Okay, so next thing we're going to do is we're going to take another break, digest this for another 10 minutes, and then we'll be back here, 3:55, right? Let's come back here at 3:55, and we'll continue after. All right. Let's come back. We're going to go through another notebook number 4. Notebook number 3, by the way, was basically the most intellectually demanding notebook of the tutorial, right? So everything from this point, it just goes downhill from. No, sorry, it gets nicer from this point. It goes downhill in intensity from this point onwards. All right. So we're gonna look at in this notebook, we're gonna look at what we would call unique structures, special structures that we can look out for inside a graph. All right. And so what I'd like you to do is to open up notebook number 4, right? And in this notebook, we have a physician trust network, okay? This data was collected in 1966, so this was like old-time America. This network captures innovation spread, basically. And so each node represents a physician, and an edge between two physicians shows that the left physician told that the right physician is his friend, or that he turns to the right physician if he needs advice or is interested in a discussion. So this is a bit of a social network, except with the edges defined a little bit more fine-grained, all right? There always exists only one edge between two nodes, and that's a rule. Even if more than one of those listed conditions is true. Okay, all right with that? So let's load that data set, and I'd like to have y'all execute the cell right below and make a Circos plot of this chart. And I'd like to ask, from looking at this Circos plot, what can you tell about the graph? It looks like there's two separate networks. Okay, it looks like there's separation. Anything else? Maybe it's one big one and 3 small ones, given the structure of the connectivity, right? That could be true as well. Once again, if we made this a hairball, I'm wondering what we could tell. we can tell something that there are 4 networks. So this is maybe one of those rare situations where the hairball would be interesting, but you couldn't tell much more about the local structure inside each of those hairballs, right? So the local structure inside of the hairballs could be interesting as well. We've totally obscured it by drawing the hairball. However, we may have been able to still grok the fact that there might be four groups of physicians. And it sort of makes sense, right? There were 4 towns. And this is 1966 United States of America. And communication wasn't as good, right? So, networks tended to be within the same town and not across towns. So maybe that's a real thing. All right? Okay. We're going to use this graph. We're not going to really analyze it, but we're going to use this graph as a leverage to sort of think about how we find interesting structures, okay? And so one of those interesting structures is a clique. We know about social networks, right? Social networks. How would you define a clique in a colloquial sense? Any volunteers? This is not a trick question. Sorry? Frequency of interaction, okay. An exclusive group, like they hang out together, but then... Pardon me?
There's a clear boundary.
Yeah, they're kind of isolated from each other and they don't let others in and stuff like that. Yeah, okay, sure. So the graph theoretic definition of a clique is highly inspired but not identical to that definition. The definition of a clique is a set of nodes that are, a set of 2 or more nodes that are connected to themselves such that every member of that set is connected to every other member of that set, okay? So that raises a few questions. What is the simplest clique that you can ever find? Sorry? 2 nodes connected by an edge. That is the simplest clique you can find. So let's make it a little bit more complex. What is the simplest complex clique that you can find? A triangle. Yeah, a triangle. 3 nodes connected together in which all of them know one another. Okay? Is that all right with everybody? Cool. So one way that we can find, one structure, that is very interesting is a triangle relationship. You all know about LinkedIn, right? And LinkedIn was actually the first to implement a friend recommender system. That friend recommender system is actually based on looking for triangles that almost but didn't exist, right? We'll get to that in a moment. So, but one thing you can look for is therefore, where are the triangles inside the graph? If you can find all of the triangles, you've basically been on your way to find interesting structures inside that graph. So how do we do a triangle finding thing? Well, we can ask maybe a slightly related question, which is a node in a triangle? And if it is, then maybe we'll be able to find all of the triangles. So one example of triangle finding looks something like this over here. What we do is we look at every single, we take a node and we take a look at all of its neighbors. We know that by definition, if a node is in a triangle relationship, then all of the nodes in that triangle, the other nodes in that triangle must be neighbors of that node, right? It's a trivial property of a triangle relationship, okay? So we can iterate over every pair of neighbors of that node and ask, does an edge exist between the 2? And if it does, then we say, yes, that node is in a triangle relationship. Does that make sense? So that's essentially the logic behind what's going on over here in this code cell. So if you can run that, you'll see that. So now, what Network X does, however, is like one of these. It's one of those situations where I wrote something that I can easily solve with built-in Network X functions. So actually, Network X has an nx.triangles function, and we know that it returns an integer, and we know that non-zero integers evaluate Boolean as true, and 0 as an integer evaluates Boolean as false, right? So you can actually do if nx.triangles g comma node and get back already, is it in a triangle relationship, right? You can do something like if nx.triangles of that, right? So that's definitely something you can do. Okay, so I'd like you to attempt the exercise below. What that exercise asks you to do is to return for every node that is inside, for a given node, return a list of itself plus all other nodes that it's inside a triangle relationship with. And what this is useful for is you can actually grab just that subgraph out and visualize that, right? So I'd like you to try implementing that function, right? And this will give you, again, practice with thinking on a graph. Okay, how are we doing? If you're done, give me a thumbs up. Right, we're roughly at the place we want to be. So, if you implemented it correctly, you should have something that looks like this. We iterate over every pair of neighbors that node has, and we ask if if an edge exists between my neighbors, then we'll add it to the set of nodes that are in a triangle relationship. And then finally, because the requirement of the function is to add also that node itself, we have line 12 over there, okay? And then we'll get, something like that looks like this. And we can actually draw out the fact that, yes, these are the only nodes inside a triangle relationship, because if we also extend it to the nodes that are just the neighbors of node number 3, we have a few other nodes that are present that are not inside a triangle relationship, all right? Do we have any questions on this? So far, so good? Okie dokes. So I'm going to switch over to drawing mode because this now is an interesting idea. This lets us take a look at the foundations of how friend recommendation systems on social networks were implemented. Okay, so let's think about this guy over here. So you have the open triangles problem. And what does an open triangle problem look like? Basically looks something like this. A is connected to B, and A is connected to C, but B is not connected to C. So what should we do? Maybe we should close the triangle, right? Right, and this is what they call, I think they call this triadic closure. Is maybe what you would find as like the technical term that describes the first implementations of friend recommendation systems, okay? And, you could maybe even bolster that information by saying, well, A is also connected to D, and but C is not connected to D, so then maybe like, C is also connected to D, so we've got that kind of relationship, but, that last edge is kind of missing, right? That last edge up here is kind of missing from the picture. So maybe we should recommend that these two be connected, because the missing edge from a clique, the missing edge from a clique is even more evidence that the missing edge from a potential clique is even more evidence that, hey, those two probably should have their offline social relationships reflected online. Kind of big brothery. But yeah, sure. We'll accept that for the moment. All right, do we have questions on that? Yeah? Everybody get that? Okay, so what I'd like you to do then is try to write this implementation, right? Do the open triangle finder. Find out which triangles are open at the moment and may want to be closed. So give that a shot. Okay, another pulse check. How many of you are done with this one? Okay, that's about right. If you're not done, we'll go through the answer right now. This one is basically a mirror of the previous exercise, right? Or a previous function that you saw, right? Where we're implementing if it has an edge. If my neighbors have an edge, then I'm in a triangle relationship with them, right? So now in this particular case, we're looking for the open triangles. So if my neighbors don't have an edge between them, then yes, we are in a triangle relationship. So line 13 in this code cell is the most important line that implements that logic, right? I wanted to switch back into drawing mode so that I could show you actually the two types of scenarios that we can look for whenever we're looking for triangle closures, right? So if we switch over to drawing mode, you'll notice that there are two scenarios. There's the scenario, let's let that come up. There is the scenario where we have the node that we're querying being the middle node of that open triangle, right? And that's the situation, that's the scenario which you all implemented, okay? There's also the other scenario, which is this one on the right, which says that the node of interest is actually the terminal node. So in this particular scenario, how would you find whether it's in a triangle relationship with this guy over here? What's the logic that you need to follow? Yeah, so I have to start here, find my neighbor, and find my neighbor's neighbor, and then ask, is the neighbor of my neighbor a neighbor of myself? Right? And then you'll have the logic is if the neighbor of my neighbor is not my neighbor, then we are in an open triangle relationship. Okay? Are we okay with that? All right, cool. Don't worry, I'm not going to have you implement this because that's the more complicated scenario. Okay, so we talked about triangles, finding open triangles, a little bit about their application. Do we have any questions yet at this point? Okay, if not, move back to cliques, okay? Because cliques are the interesting structures that we want to think about. Again, we're going to mostly use visuals first and then try to move into code. There is this concept of what we would call a maximal clique. And I'm going to try my best to draw out an example. Let's start with this guy. Okay, we have this graph over here. What is so clearly there is there are a bunch of cliques inside here. Can you find them? If we were to enumerate every single clique that exists, how many cliques exist inside here? I'm going to label the nodes B, C, D. How many? 5. And why is that? We have the clique AB. We have the clique AC, BC, DC, and then ABC. Right? These are all of the cliques that exist inside this graph. So there is this idea of what we would call a maximal clique. And if I remember the definition correctly, the maximal cliques are defined such that we cannot add in another node in the graph that would expand it to be to expand it any further, to expand the clique any further. Okay, so if we look at the cliques AB, AC, and BC, oh, Siri, there's no NBC on my iPad. AB, AC, and BC, those 3 of them can actually be subsumed under the graph, the clique ABC. Okay, in this example. Does that make sense so far? So therefore, the maximal cliques are actually ABC and DC, and nothing else. Okay, any questions thus far? This is kind of neat, and there's this very neat graph theoretic property that I've kept in my back pocket but never had to use yet, but I foresee I'll use it in some applied situation. That is, every clique of size k can be decomposed into its clique of size k minus 1. So the simple example here that we can see is that every triangle can be decomposed into its edge set of edges. Meanwhile, every 4 clique, that is 4 nodes that form a clique, can be decomposed into 4 triangles. If you don't believe me, we'll redraw this one. A, B, C, D, right? We got the 4 clique over there. It can be decomposed into, this is into ABD, BCD, right? ACD and ABC. So this is a very neat property of cliques. Every k-clique can be decomposed into its k-1 clique. And by the way, every k-1 clique can be decomposed into its k-2 cliques up to the point where k-n is equal to 2. Right? Are we okay with that? Yeah, that's a neat property. So we're going to switch back to notebooks. And there's a final exercise on cliques, which I'd like you to attempt. It hopefully isn't too difficult to attempt. All we're going to do is we're going to find cliques, and network X has a find cliques function. Okay, and in network X's find cliques function, it will find all of the maximal cliques that exist inside the graph. All right, it'll find all of the maximal cliques. So then, really, we can then filter this list of maximal cliques for a particular maximal clique of size k, right, and restrict ourselves to that size of clique. So I'd like you to try that exercise below. It shouldn't take you too long, unless we're all kind of brain fried. Then, if you're feeling lazy, follow along and see how I do it up there. Okay. Okay. So your first line should be something like, let's find all of the cliques, the maximal cliques that exist in a graph, and put them inside a list. And the second line would be a return statement that tells us, here, give me all of the cliques if they are of the particular size we've pre-specified. We okay with that? Now, the list of maximal cliques of size 2, is that equal to the number of edges that are present? It shouldn't be, right? Because some of those other little edges are subsumed in bigger cliques that are of bigger size. So this would be only the edges that form a maximal clique. Okay? Cool. So the next thing that we're going to go into is this notion of this other structure called a connected component. Now, if you remember, in nx.draw of g, we had basically 4 subgraphs, right? And between those 4 subgraphs, there were no connections to one another, right? So we don't see cross-group connections over here. So we can actually identify each of those connected component subgraphs. So each one of these forms a connected component subgraph. Are we okay? And network X provides such functionality. So if you do this, next cell below, then you'll find the connected component subgraphs of graph G. And that's useful for finding completely disconnected sets of nodes. And then maybe you might want to be able to pick those out from the data set. And I actually use this at work in this thing where we had these experiments which we wanted to compute covariance matrices on, but we couldn't compute covariances for all of those. So we actually used so in order to figure out which set of experiments we're able to use in this new algorithm which we're developing, we actually built a graph out of all of those experiments. It's an experiment by experiment graph, right? And if we could build calculate a covariance term between the two, then we said, okay, cool. Then we'll put an edge there. And so finding the connected components was intellectually interesting, like exploring that graph. Also, we used the idea of cliques to find densest, to be able to find out what other experiments we're able to use, right? So it's a very productive use of cliques and connected components in real life. I'm glad I work at Novartis. It's a real fun data playground. So this exercise below, we're going to actually color that Circos plot by the connected component subgraphs. I understand people are getting to their limit, so we'll do a lot of follow along coding. All right, so I'll type on the screen, talk through what we're doing, and then you can fill it inside your notebooks. All right, okay. So in order to get NXVis to be able to color nodes by which connected component subgraph they are, we have to sort of assign an identity to each connected component subgraph. And one way we can do this is by simply assigning it an integer, right? So you can do something like, well, let's get all of the connected component subgraphs, and now let's iterate over each of the connected component subgraphs, but also grab an index for each of those connected component subgraphs by using enumerate. Then we'll simply iterate over the nodes, and in small g.nodes, now in the big graph that we're going to plot, g.node n add a new sub metadata entry that is just the index of that connected component subgraph. Okay? That's what that will look like. And we'll then tell NXVis node color by subgraph and node order by subgraph as well. And that should give you a plot that looks something like this. Okay? Are we cool? And so clearly we can see now the 4 connected component subgraphs. There's the big green one, and then the smaller, roughly equal-sized orange, maroon, and gray. Okay? And one thing that does become kind of alarming is how the U.S. Congress is slowly becoming two disconnected subgraphs, right? Yeah, maybe I should go back to Canada. All right, cool. We're going to end Notebook 4 on this very light note. This point, I think, is a great point to do a small discussion amongst yourselves first to share something new that you've learned up to now. So 2 minutes. Go ahead. Okay. Anybody want to share something new they've learned to this point? I think it's always useful to bring that out, right? Like, it's both feedback for me on how we're doing, but also reinforcing what you've learned. Anybody? Wow. That's too much. The scope is too much for that one.
I thought the relationship between, having foods and how that's going to relate to like control complexes and
Oh, okay. Yeah, okay. I accidentally made that connection then. That's awesome. Cool. Anything else? Come on. Or do I have to start pointing at people blindly? Anybody on this side?
All you do is to actually visualize some of these things now.
Yeah. Yeah, definitely. Part of the motivation was I was also myself having, like when I first implemented Hive plots, man, that was a lot of lines of code, right? But then I looked at it one more time and then it was like, oh yeah, that there's a bunch of stuff that can be wrapped up in a nice API. So yeah, that was definitely, thanks for bringing that up. Anything else? Anybody else? Someone at the back? Okay, I'm gonna point at someone, right? So my leftmost on the back row. Do you have anything you want to share?
I pretty much vote with the guy that said everything. Knowing nodes and edges and grouping and everything.
Okay, cool.
Fire nodes, but it's great.
Cool, awesome. All right, well, the fact that there are a bunch of people that say everything means there is a place for someone to teach network analysis, so that's really awesome. Okay, cool. All right, we're going to move on to some more pragmatic things now. Okay, so we're going to talk about notebook number 5. This is a question that always comes up, which is how do I actually load graph data into memory and then convert it into a NetworkX compatible format so that I can then do all of the nice manipulations in NetworkX. So I'd like to invite you to open notebook 5. This notebook thankfully, is much more me just talking, so you really don't have to code that much. And I recognize, it's 5 p.m. and you probably, most of you probably have had like, this is the 4th tutorial, right? So the fire hose of information is very real. So what I'm going to do is I'm going to talk you through some concepts first again, and then some of the code, example code that you can use. So once again, I'm going to switch over to drawing mode, and because I think it's really important that we see the mapping from the NetworkX data structures onto things like tables and pandas data frames. Okay. So if I've got my nodes, okay, my node set, and I've got my dictionaries, and I've got metadata that's attached on there. You'll notice if we structure our data correctly, we should actually have the same keys attached to every single node. And what does that mean? It actually means that the node set can be represented as, oh, there we go again. My apologies. Actually, hold on. This will guarantee I never hit. There we go. So what this tells us is that this can actually look like a table of some sort, right? In which we have, this is interchangeable with a format that looks something like this. Does that make sense? Does that make sense? So a node list with all of its metadata can actually be a pandas data frame in memory, which has as its index, or even not just as an index, as a column, right? You would put as a column of data that is the node ID, and then all of the metadata out there. Okay? This actually means you can if you think carefully about it, this also means then that you can store your edge data as a table. Why so? Because we have node 1, node 2. We have the metadata attached to it. Okay, so we have that. That is again interchangeable with another pandas data frame that looks something like this. Okay? So really, every graph, we say that every graph has a node set and an edge set. Another way of thinking about it is if you've got graphs that have metadata, then this graph has a node table and an edge table, right? Every graph has a node table and an edge table. And if you maintain those two tables in memory, you've got a full description of the graph. Okay? Are we all right with that? Okay, so we're going to see how we can do that with NetworkX. All right? So let's go back to coding mode. So we're going to open up notebook number 5 and basically see how we can represent our data as two pandas data frames. So if we think about, how many of you live in the Chicago area? Right, so Divvy, sounds familiar? Yeah, it's the bike sharing system. Boston's got its own, it's called Hub Bikes, it's pretty awesome, much better than the MBTA. And these, we can actually record these bike trips that occur between bike stations, and that forms a graph, right? A graph of trips between bike stations. So the nodes would be bike stations, and the edges would be trips, and now we have a choice, a modeling choice actually. I intentionally didn't say this, but you can actually allow for multiple edges that have distinct metadata between nodes, and in Network X that is implemented as a multi-graph or multi-directed graph, multi-digraph. Now, if we're faced with something like the Divi data set, which has hundreds and thousands of trips recorded with possibly thousands of trips between any pair of nodes, one modeling choice we might want to do is simply condense the number of trips and record it as a single edge if we didn't want to worry about multiple edges existing between a pair of nodes. Are we okay with that? So that's a modeling choice that we can make. So we're going to read in the two data frames. They look something like that. Now, Network X has some built-in functionality that lets you take a table that looks like the edge list, all right, the edge table. It lets you take the edge table in and construct the graph from it, but then you still have to attach the metadata for the nodes because the node metadata doesn't exist. Okay, but the edges, the heart of a graph is the edge set, so it's more important to get that metadata in first, and then we can talk about the metadata for the stations later. So one way to do it is to use the Network X machinery. I prefer actually to instantiate the nodes first with the proper metadata. So then adding in the edge data becomes the second thing. It's just the way I think, okay? So I'm going to show you that way. One way that we do it, the way we do it is we instantiate the directed graph over here. And then all we do is iterate over the stations list, the stations data frame. We can do it this way, where we say stations.toDictionary, right? We convert the entire pandas data frame to a list of dictionaries, and then add in the node as the node ID, and then pass in the rest of the rows, rest of the columns as a star, unpack the dictionary kind of way, okay? And then that automatically, if we run that, that gives us all of the nodes plus all of the metadata that's associated with it. And if you run that in your notebook cells, then you'll have that information nice and big on your laptops. Okay? Then, like I mentioned, we might want to do a modeling choice where we group the multi-edges into a single edge, right? Because each of these trips records possibly multiple trips between any pair of nodes, right? So one thing we can do is then instead take the trips and group them by their from station ID and to ID, and simply count and simply get back the counts of the number of records that exist in that particular group. Then all we do is iterate over that new counts table and add that edge data into the graph. Are we okay with that? So far, so good? Okay, we're going to skip the exercises because they're just there to reinforce some ideas. One thing that you might find of interest is, for those of you who are in the Chicago area, you'll recognize this layout, right? That's basically something that looks similar to Chicago. So if you go down and go to run one or two cells like this one, and then this one. You can actually, when you're drawing, now if you do it right, you can actually take advantage of the Network X drawing capabilities to exactly position nodes at the right places that you want. Okay? And then that can give you a visualization that looks something like this guy, which has all of the stations plotted, but we also have all of the edges plotted inside there. And right now we have only those edges that have 100 trips, show 100 trips or more, right? So these are the most commonly traveled routes over that time period, right? So you can do things like that. That's definitely a possibility. Now, if you have geographical graph data, it's actually really handy to be able to take advantage of the longitude and latitude information that's inside the graph. Okay? Cool. Finally, how do we save NetworkX graph files? Because these are nothing more than objects in memory, pickling is an option that's available to us. So we can take a graph and pickle it to disk and then read it back, right? So that's totally allowed. Of course, never open a pickle file that you don't know where it came from, right? So make sure that this is the pickle file that you actually made. So don't forget to do things like compute the hash of the pickle file, make sure that the hash is the correct thing before you open it up, okay? They're just some minor security things, just so that you don't accidentally run a piece of Python code that executes rm minus rf /, okay? So yeah, you don't want that to happen on your computers. Okay, so that's notebook 5. Do we have any questions about how we can represent graphs, tables, NetworkX, pandas, etc.? Let you think about it for a few seconds. Okay, looks like not. Let's see, the next notebook we'll go to then is one on bipartite graphs. So I'd like to invite you to open up notebook number 6. Once again, I'm kind of getting addicted to this drawing thing, so I'm going to switch over to drawing mode. We'll talk a little bit about bipartite graphs. So bipartite graphs, where do they come from? Where does the name come from? Well, it comes from the idea that we can take our node set and partition it into 2 groups. Okay, so bipartite graph comes from that idea. And so you might have part of the node set over here, and part of the node set over there. Okay? And one unique property of bipartite graphs is this. Edges never exist between nodes of the same partition. So that edge never exists. Instead, edges can only exist between nodes across partitions. So you might have a graph that looks something like that. Are we okay so far? So, discussion question. Where do you think bipartite graphs might show up? Were you in the deep learning tutorial? Neural nets. His answer was neural nets. Yeah, I'll dig that. Where else?
When your nodes represent 2 different categories.
Okay, do you have a concrete example?
One could be like sports teams, and the other could be athletes that have played in various sports teams.
Okay, cool. That's one example. Do we have another example? How would we have different categories? Ah. Okay, cool. For the sake of YouTubers, I'm not going to record that one. But I understand where you're coming from. I totally understand where you're coming from. How about here?
Companies and customers.
Companies and customers. Yeah, okay. And do we, what would the edge relationship represent then?
Well, so say I'm a customer, and I shop at,
This particular Macy's, yes.
I shop at Nordstrom's.
Yes.
But I don't shop at another customer.
Right, exactly. Yeah, thankfully you mentioned that we're out of the age of slavery, right? So people don't buy people. Good.
Games and players.
Yeah, games and players. So that's another good one. So the edge relationship would be defined as, yeah, I play StarCraft. I really do play StarCraft, but I don't play anything else, right? So yeah, there we go. Sorry, just revealed something. Very personal. Anything else? Teachers and students. That's a very unique, where did it come from? Okay, so teachers and students. That's a very unique one. It is categorically correct because in a particular classroom, teachers are the teachers and students are the students. But then, of course, over time, sometimes the students can then become the teacher of the teachers if they do something. But then I hear where you're coming from. So yes, let's record that one. Under very limited circumstances, teachers, students can be a valid bipartite relationship. Okay, cool. So we've got examples. I'm going to harp a little bit on the e-commerce example because I think it's one that we can relate to on a day-to-day basis. Okay, and I'm going to bring the example of customers on one side and products on the other. Okay. So first question relates to the adjacency matrix of the bipartite graph. Right? So is this adjacency matrix going to be guaranteed to be square? Pardon me? No. And what is the reason why? The reason is go ahead. That's right. The number of customers and the number of products might be different. The way we arrange a bipartite graph as an adjacency matrix is to put number of customers on the rows, number of products on the columns, or you can transpose it. Okay? So that's the first property of an adjacency matrix for the first property of a bipartite graph. The next property that we can think about, so this is the adjacency matrix. And the next key property that I want everyone to take away from this tutorial actually is about what we call a projection of a graph. Okay? So let me see if I can copy paste this thing down below. Apparently not. So I'm going to just redraw it. If we have a bipartite graph that looks like this, then we've got the customers and we've got the products. And I've got a simplified graph over here, all right? We've got those relationships. We can actually create what we call the projection of the graph onto one partition. That is to say, we create a new graph. Say we want just the customers graph or the products graph. We want to know how customers are related to one another on the basis of their shared purchases. So how would we construct that graph? The way to do it is we would take this particular customer. Can you see the yellow? Is it not so clear? Not so clear. Let me try again. Let's take this customer, okay? We want to know what its relationship is to this other customer. We trace a path that way. Are we clear on that? We trace a path that way, and that gives us customer A, B, C. That then gives us the customer by customer graph. A is connected to B, right? And how is B related to C? Well, B is related to, and actually, by the way, sorry, we might want to put a weight on this because there's one path to go from A to B. So we'll put 1 over there. Okay, so let's think then about the path from B to C. How many are there? There are 2 of them. This one and that one, right? So we'll do, oops, B to C, and we'll put a weight of 2 on there. Now how about from A to C? There's only 1, so we'll put a weight of 1. Right? Are we clear on this? All right, so let's see how we can take a look at this, how we can construct a bipartite graph in Network X, and then how we can compute things like the projection and the adjacency matrix and the likes. All right? So if you open up notebook number 6, we'll load in this thing called the crime network. This data set has 2 node partitions. The first node partition is people, and the second node partition is crimes. And we put an edge between the two if a person was related to a crime as one of a victim, suspect, witness, or both at the same time. All right? So that's what the data set is about. And it's nice because then we have this clear node partition, edge partition. So if you look at the node set, there's a special keyword argument that is reserved to let Network X identify what partition this node belongs to. And that keyword is bipartite. It must exist inside the metadata dictionary. All right? So if you create a graph and you add a bunch of nodes and you add the bipartite keyword, suddenly all of the bipartite algorithms that are inside Network X are available to you. Okay? Now, it being bipartite definitely guarantee that there are only 2, right? There are only two partitions. So if you, in your node set, you suddenly have 3 partitions, then like it confuses the algorithms. So it's up to you as the end user to ensure that you have only 2 partitions inside your, two labels for your partitions. Okay, so how do we compute a projection? There is this particular algorithm function called Network X has the bipartite submodule. It has the projection submodule, and in that submodule, it has the projected graph function. And that projected graph function takes in a graph, but it also takes in the node set for which we want to create the projection onto. So if you remember back to the drawings that we had just now, in order to know which projection we want, we have to first pre-specify the node set for which we want that projection to be made. Are we okay? So far so good? All right? And that's how you can get something that's how you can get your projected graph. Person graph in this case, PG. Right? We can have the crime graph by doing a similar thing over here. Are we all right with that? Cool. The other thing that I wanted to, I forgot to mention this one actually. All right, so let's go back to drawing mode. And then think about the semantic definition of degree centrality. Okay, so who remembers the definition of degree centrality?
Number of neighbors a node has divided by the total number.
Yes, the number of neighbors that a node has divided by the total number of neighbors that that node possibly could have, right? So that's the definition of degree centrality. In a bipartite graph, how does the denominator change? Say, for example, if I'm on the blue partition, let's say, for example, actually, I'm this node. How many possible neighbors could I have? 3, and that comes from meshing the definition of neighbors with the definition of degree centrality with the definition of a bipartite graph, because the total number of neighbors that I can have is the total number of nodes on the other partition. Okay? So that's something that changes. So if we were to ignore the colors on this graph, the denominator would be 7 or 6, depending on whether self-loops are allowed, right? Now it's only 3. So number of edges divided by number of nodes on the opposite partition, okay? And so network X, if you look right at the bottom of that notebook number 6, it has a bipartite degree centrality algorithm, okay? And that tells that gives the degree centrality for the nodes in just that partition, okay? And it's going to be a different number from the vanilla degree centrality that we're used to, okay? All right, that ends the notebook on bipartite graphs. We're going to do one final thing, which is on matrices. This is one of the latest, newest pieces of content that like I grokked and got into my head about 1.5 years ago. And ever since, it's been like very eye-opening to just see this, okay? So we're going to look at this guy over here and see how we can actually do some interesting things like message passing operations or bipartite graph projections and cast them in terms of linear algebra operations and actually get pretty interesting speed ups on what we're trying to accomplish. Okay, so first thing I want to look at, okay, is basically a toy example. So open up notebook number 3, bonus notebook number 3, and you'll have this graph that looks something like this. Okay? Oh, sorry. Yes, thank you. I have to switch back to coding mode. Do you all have something that looks like this on your screen? Yeah? You have the linear chain. Right. What does this graph look like in matrix form? Looks something like that below. Right? That's the adjacency matrix of the linear chain. Now, you can take a graph and turn it into a NumPy array by using the nx.toNumPy array function. And that will take that graph and it'll order the nodes in the correct order and give you an array that looks something like that. And that basically, by the way, is the underlying implementation of the matrix plot in NXViz. So that's just a little tidbit. Okay, so if we do the matrix power of the adjacency matrix, we get some interesting properties. You can do something that looks like this. And what does that give you? It gives you a new matrix, but it's got some interesting properties. This property is, oh, do we have someone who knows this? Not really. Okay, no problem. Guess, take a guess.
Is it the number of ways you can choose it?
Right, it's the number of ways of getting from one node to another in 2 steps. So an edge is defined as the number of ways of getting from one node to the next in 1 step. So I, by definition, cannot come back to myself in 1 step, but I can get to my neighbor in 1 step, but I cannot go 2 degrees out in 1 step, right? So now in a linear chain, you'll notice the diagonals are 1, 2, 2, 1, okay? And that is the number of ways of getting from my neighbor, from myself to my neighbor and back to myself in 2 steps. And how is that? There's only one way to do that if I'm at the terminus, okay? And there are 2 ways to do that if I'm in the middle. I can go out 1 and then back, or I can go in 1 and then back. And that, by the way, corresponds also to the degree of the node. So if you want to find very quickly in matrix form the degree of the node, take the adjacency matrix and do the power and then grab out the diagonal, and suddenly you now have the degree of every single node. We okay with that? So far so good? No? Mind-blowing, right? Okay, cool. So yes, so we can grab out the diagonal and get back the degree. And that's 2 ways of looking at what the degree is. It's the number of neighbors, but it's also the number of ways of going from one node to the next and then back to myself. right? They all follow the same definition. Right? They're all sort of similar things. So then the kth power. What do you expect if we take the third power? What will the diagonal be? Oops. Pardon me?
3.
So yes, and if we take 3 steps, what will the diagonal of the adjacency matrix be? It should be 0. Why? Exactly, you cannot get back to yourself in 3 steps by definition. So that's another really interesting thing that we can find. So if now we had, so that was all done for an undirected graph. Okay? Now what if we had a directed graph? And we made it a directed linear chain that looks like something below here. Okay? So if you run the cells up to there, what do you see? You see a graph that says we can go from 0 to 1, but not 1 to 0. We can go from 1 to 2, but not 2 to 1. And likewise for 2 to 3. Are we okay with that so far? So far, so good? So if we do the array, numpy array form, we get something like, we don't get a symmetrical adjacency matrix, right? So far, so good? Now, what happens if we do the second power? Should we expect to see the degree on the diagonals? So think about it on a directed graph. How many ways can I get back to myself in 2 steps in this particular example? There's no way, exactly. There's no way I can come back to myself on this directed graph. Because in 2 steps, the only way that I can go on this particular graph is from 0 to 1 and then 1 to 2. All right? So that matrix reflects that exactly. And likewise for node 1 to 2 and 2 to 3, so we can have something from 1 to 3. Okay, so that's a little toy example. Next thing we're going to do is we're going to try this social network thing. So the fact that we're able to calculate, calculate these matrix powers is kind of interesting, because then it lets us do, it's got analogies to like message passing on a graph, right? How do I get a message from one node to the next, right? And so we want to know how many ways we can do it. We can do the matrix powers actually, and get back the number of ways that we can do it. Do that message passing operation. So we're going to try this out with the university social network. It's from Australia. Ratings of one friend to another, right? Just something like that. And the matrix plot looks like that. Where do I want to go here? I want to go to message passing. Okay, so message passing. Once we know about the matrix operations on the adjacency matrix, now we can think about things like that. So if I've got a message that lives on node 0, and I want to move it to node 1, and then to node 2, and then to node 3, right? You can simulate that with Python code, right? You can sort of explicitly simulate it with a for loop plus like ifs and conditionals and the likes. But it turns out there's a really compact mathematical way to do message passing. It's done by matrices. Okay, so the way that it works is we take this array. We create an array. And that array has ones where the message exists and zeros where the message does not exist. Okay, so we're still on the linear chain example. Message now has this particular shape, which is it's a column vector. If we take that column vector, which is what is the column vector shape? It's this doesn't look right. It's 1 by 4. So 1 row with 4 columns. So it's a row vector. My bad. So if we take this 1 by 4 thing and we matrix multiply it against the adjacency matrix of this directed graph, now we've copied the message from node 0. We've moved the message from node 0 to node 1. Did everybody see that? The resultant array is 0, 1, 0, 0. That matrix multiply does that. Okay? And if we take message 2 and multiply it one more round by that adjacency operator, now the message has moved from node 1 to node 2. And we can do it one more time. And find that the message has moved from node 2 to node 3. 0, 1, 2, 3. Right, so 4 rounds of message passing efficiently implemented as a dot product, effectively. That, for me, was mind-blowing the first time I tried it out. Okay? How many of you are feeling mind-blown right now? Okay, yeah, the fact that linear algebra can be used to this degree is, for me, always fascinating. Okay? So, my brain right now is a little muddy, so I don't think I could give you a clear answer, but I do know why it works. It relates to, it relates to how we do dot products and the likes, but we can talk about it at office hours. Okay? So we can actually write a function called propagate, which allows us to propagate a message from a starting node to its neighbors and so on. And we can make something that looks like, seriously, like it would have been an animation that which the yellow dot moves to the next one, to the next one, to the next one. Wondering if I can switch over to Binder and solve this problem. Actually, Bobak, do you have... actually, no, I'll be okay. I think I'll be okay. I think the animation generally works in Binder. Cell, run all above, and then run this one. It should be pretty fast. Oh, wow. Okay. Technology conspires to not work with me today. But if you run it, if you're able to run the notebook locally for yourself, you should get that animation running on your own machines. And you will see that we have the message passing operation happening, and it's just working. Okay? All right? Cool. So you can then do the same with the university network and see how message passing happens over there. Okay? Now the last demo before we end, this you don't have to talk about. This one you don't have to live code, is about how we do projections with linear algebra. Okay, that's like one of the funnest things. Another really fun thing. So if we come back to the customer product sort of analogy, we create this like really toy matrix, adjacency matrix that says there are 4 products and there are 3 customers, and we want to build the projection of the customer product matrix onto the customer partition. Instead of using Network X's bipartite module, you actually can take the adjacency matrix of the bipartite graph and dot product it against the transpose of the adjacency matrix. So that's what we're doing over here, right? So we're taking the 3 by 4 thing and dot producting it against the transpose, which is 4 by 3. And what we get back is the customer matrix, which should be 3 by 3. The diagonal has this neat property in that it actually shows the sum of products, the number of products that customer purchased, which is exactly correct. If you look at it, this customer 0, the first row, purchased only 1 thing. The second row, second customer, purchased 2 things. The third customer purchased only purchased all 4 things. Right? So it's a very neat property that comes out. In addition to that, the off diagonals tell us which customers are related by shared purchases. So if you look at the columns and you sum up, customer 1 and customer 2, they are related by 0 products. Customer 1 and customer 3, they're related by 1 product, right? Just 1 is overlapping. Customer 2 and customer 3, they're related by 2 products. There's this one and this one, right? Those 2 overlap. Okay? So that's like a really efficient way to get a lot of information from the adjacency matrix alone. And you can do the same by doing the product matrix by first taking the transpose of the adjacency matrix we have here and multiplying it by the adjacency matrix. And then now you have the product by product projection. Now you'll see which products are similar to one another on the basis of which customers were purchasing them. Okay? And so the final thing that I want you all to see is this. We can have these really large graphs. Okay? This graph is like, I forgot how big it is, but it's at least tens of thousands of reviews on products. So you have people who left a review on a product. If we use, okay, so I'm going to very quickly do the object-oriented versus the matrix form to compute projections. So if we run this, this should take about 25 seconds. This is using NetworkX's built-in function. Okay, we'll let that run for a little bit, and then we'll compare how fast that runs against the matrix form. Clearly, you know the answer. The matrix form is going to be faster. It's going to be much, much faster to compute. But there is, of course, a trade-off in code readability, right? So if you look at this, ooh, we're using quite a bit of like NumPy stuff to get what we need to do done. So unless we wrapped all of this code inside a nice single function call that is very, descriptive, someone who looks at this would go like, what in the world are you doing? But notice, this thing took like 15.77 seconds to finish computing with by the way, most of the compute time spent inside here, this part, whereas down here, the compute time was like 0.4 seconds. So what's the speed up there? It's about 30 times faster, right? And so if you know the matrix math that expresses what you want to do, computers are actually really, really optimized to do that sort of thing, linear algebra. And so if you can cast what you're trying to do inside NumPy code, into NumPy code, that's actually really powerful. That's a very, very powerful thing to be able to do. And you'll notice we actually were hunting for basically the most similar customers between on the basis of like shared purchases, right? And it would have been very difficult to find out which pair of customers are most similar if we had an even bigger graph, right? That was more massive than this. So, one of the things I regret not learning in undergrad was linear algebra, right? Now I'm relearning it post undergrad. Encourage everybody, join me on this journey to learn linear algebra properly, because it's a really useful and handy tool that shows up in multiple places, right? It shows up in deep learning. It shows up in graph theory. It shows up also in Bayesian stats as well, right? So it's a really, really powerful thing to be able to learn and have that as part of your toolkit. Okay, so final thing we want to do, I'd like to give out this little thing to everybody who stayed all the way to the end. Babak has it in his hands. If you were at the Bayesian and the deep learning tutorial, you know that this is like a little congratulations card that says, thank you for coming, thank you for finishing. I'll help out, give it out as well. Oh, thanks, Hannah. It's also a little bit of an ask from you all. There's a QR code on the back. So if you prefer scanning things with your phone, you can actually give feedback on how the tutorial went. If not, on the NetworkX Network Analysis Made Simple repository, there is also a link right at the bottom that says, please leave feedback. So really would appreciate you leaving feedback on how the tutorial went, what was useful, what was not useful, how we could improve the teaching style, etc. This has been done, even though it's been done more than 8 or 9 times now. I still always appreciate the feedback that tells me how I can improve it for next year. And Riddle, who is usually my co-instructor, he also takes note of that feedback and incorporates it into his next round. So I'd really really would like to encourage you to leave us feedback, tell us how we did. Other than that, if you are interested in talking more about data science and the toolkit that we've one might want to have, Bayesian stats, deep learning, network science, traditional machine learning, et cetera, I'm going to hold office hours. They'll always be in the Tejas room, which is the room in which we have breakfast. And if you want to talk, I'd come and welcome you all to join in. And the hours are in the Slack channel. All right? So with that, thank you for staying all the way. Wish you a very, very productive Scipy conference. And I hope to meet you all in the hallway or wherever. All right? Thanks a lot.